Hello, everyone. Today we'll be discussing the solution to problem 3 from the USACO February 2026 Gold Contest. And in this problem, we're given a procedure which generates a random tree of n nodes. So essentially, we initially have n nodes and no edges. And then for each I from 2 to n, we're going to choose a random integer in the range between 1 and I minus 1 inclusive. And then we'll add an edge between node I and node x. And then after we have added n minus 1 edges, we'll choose a random permutation of the integers from 1 to n, and we'll apply that permutation to the node labels. So we'll randomly shuffle the labels of the nodes. And the goal is for a given tree in the input with n nodes, determine the probability that using the above process would generate that tree, modulo 10 to the 9 plus 7. So essentially what determining like a probability modulo 10 to the 9 plus 7 means is if you represent the probability as a fraction, it would be the numerator times the modular inverse of the denominator. So this problem requires the use of like modular arithmetic and modular inverses. So if you're not familiar with that, I would recommend that you first learn what those are and review them either on like USACO Guide or another online resource before trying to attempt this problem. But we can walk through one of the examples given in the input, which is a tree with n nodes with edges between node 1 and node 2 and node 2 and node 3. And so we can actually simulate all possible options for the trees we can generate from the above process. So in the first step of the process, for each I from 2 to n, we choose a random integer from I1 to I minus 1. So for node 2, that integer has to be 1 because I minus 1 is 1. But for node 3, we have a choice between node 1 and node 2. So there are two choices with equal probability. Either we have like this graph on the left or this graph on the right, each with probability 1/2. And then for each of these graphs, there are 6 permutations we could possibly apply. And it turns out for both graphs, there are 2 permutations which give us like the same tree as the one in the input. So for example, if we have the graph where we have edges between 1 and 3 and 1 and 2, then the permutations 2, 3, 1 and 2, 1, 3 give us like the graph in the input. And then if we have a graph with edges between 1 and 2 and 2 and 3, then the permutations 1, 2, 3 and 3, 2, 1 will give us a graph with the same edges as the tree given in the input. So you can see there are a total of 4 ways, and each of these ways has a probability of 1/2 times 1/6, which is 1/12. So the total probability is the sum of all of these, which is 1/3. And then to output this, we need to find the inverse of 3, mod 10 to the 9 plus 7. And this turns out to be this number here, because if we multiply this number by 3, it gives us 1, mod 10 to the 9 plus 7. So the answer that we'd output is this number. So solving this problem requires doing a bit of like combinatorics and math. So the first observation that we can make is for a fixed permutation in the second step, there's exactly one way we could have generated the tree in the first step so that it matches the tree that we give it in the input. So instead of like counting the number of ways to generating the tree and then the number of permutations, we can instead count the number of valid permutations for which there is a process that could have generated this tree. And then we can divide by the total. So find like the number of permutations for which the tree before the permutation is a valid tree that could have been generated by the process. And then the next observation we can make is we can iterate over like the root of the tree. So essentially, we're fixing which node in the tree was originally 1 before we apply the permutation. And this allows us to like write a condition for what tree could have been generated by the first step of this process. And that condition is essentially we have to be able to order the nodes of the tree such that all parents come before their children. So all parents essentially must have a strictly lower label than their children. So essentially the number of valid permutations is the number of ways we can order the nodes of the tree that satisfy this condition. So we've reduced this problem into computing like the number of orderings of these nodes. And so the way we can think about like computing the total number of orderings, we can think about it for each node, what are like the number of ways we can order all of its descendants. So essentially consider like a fixed node V and like all the nodes in its subtree. And assume like we already know the order, we fixed the order of all of like the children's subtrees. So to visualize this, let's say we have a node V with 3 children, A, B, and C. And let's say for each of the subtrees of A, B, C, we've already picked out an order for each node in that subtree that is valid. So where in that order, like all of the parents appear before their children. So that order, let's say, is A1, A2 through AX, B1, B2 through BY, and C1, C2 through CZ. And here X, Y, and Z represent like the sizes of each of the subtrees. Now we want to like determine what is the number of ways we can order like the elements in V subtree. So V has to be the first one in this ordering because it's like the parent, it's the ancestor of all of these nodes. But then after that, we can essentially like choose each subtree like independently, each of the children subtree independently. Essentially, out of the remaining X plus Y plus Z indexes for each of the nodes, we can choose X indexes to represent the nodes of A subtree, and then Y indexes for B, and then Z indexes for C. And we want to determine like the number of ways we can do this, which is like the number of orderings. And this is given to us by the multinomial coefficient, which you can like written out like this. Essentially, you can think of it as given like the total number of openings, which is X plus Y plus Z. We first choose X of them for the nodes in A subtree. Then out of the remaining Y plus Z, we choose Y for the nodes in B subtree. And then there's Z openings left, which we fill in with the nodes in C subtree. And so the formula for that is using this like factorial. So we take the factorial of the total number of spaces divided by the factorial of each group that we're splitting those spaces into. And so essentially what this tells us is again, like this is the number of ways we can order the like nodes in the subtree of node V if we've already like fixed the order of the nodes in each of like the subtrees of each of the children. And so this is like the multinomial coefficient for that node. And the answer would just be like the product of this coefficient over all nodes and subtrees. Yeah. So in general, like this applies to like more than three nodes. We can like generalize this with the multinomial coefficient. And it's just based on like the size of the subtree of V and the sizes of like each of the children's subtrees. And this leads us to our like next observation, which is essentially a formula that is like based off of our idea here. So if we keep track of the sizes of each of the subtrees and the children of each subtree, then this like coefficient, which we'll store in like this array comb, is essentially this multinomial coefficient based on these factorials. And like we mentioned before, the answer is the product of this combination over all nodes V. So it's like the product over all nodes V of all the ways to order the nodes uh, in like V subtree. And so this leads us to our solution idea. Essentially, we can use dynamic programming on the tree to compute like the size of the nodes of each of the subtrees. And using these sizes, we can compute like the combination for each node. And then to get our answer, we can determine like the product of this array over all of the nodes. And that will give us like the total number of valid orderings. And however, this is like too slow right now because remember, we assumed that the node of the tree was already fixed. So if we do this for each node, it will be n squared. And so the final trick to speed this up is to use a rerouting technique, which is a technique where we can solve for all roots by doing another like DP on our tree. Essentially, the key idea is if we start with a current root and let's say we want to change it so that the root is like one of the children now, right? It turns out like if you imagine this array of like combinations, the only values that change are the values at the root and at the new root because it's only determined by the size of the subtrees. And that size, um, most of the sizes don't change if you just move the root from like one node to an adjacent node. And we can use this fact to like efficiently determine the answer for all of the nodes. And then after we find the answer for all the nodes, we can just take the average because in the permutation, it's like equally likely that each of these nodes were mapped from the node one. And once we take the average, that will give us the probability that this tree was generated by the process in the input. Okay, so now let's see how we can implement this problem in C++. So the first thing I'll want to do is to define some functions that are helpful for modular arithmetic. So this is like a modular exponentiation function. So it will find x to the power of p modulo like 10 to the 9 plus 7 using binary exponentiation. And using this, we can find like a function which computes the inverse. And so the inverse, again, is x to the power of the mod minus 2. And then now we want to like pre-compute all of our factorials and inverses of factorials since we'll be using them a lot for our multinomial coefficients. So what we can do is we can have a function where we pre-compute factorials. And starting from like 0 factorial, which is 1, we can go all the way up. And this is essentially like just the definition of factorials, where it's like factorial of I is equal to factorial of I minus 1 times I. And yeah, we want to make sure we call that function at the beginning, not once per test case, but once at the beginning of like running the program. Next, we'll declare the arrays that we'll use in our DP. So this, again, will store the size of each of the arrays. This will store the multinomial coefficient at each of the nodes. And this will store like the answer if the tree was rooted at that node. And yeah, well, initially this will be set to 0. And we can do our first DFS, which is the initial DP with the root at 1. So here we'll have a DP starting at node X where the parent node was P. And we'll initialize our values. So we'll initially set the size to 0 and the number of like combinations to be 1. We'll loop through all the children except for the parent, and we'll go like DFS down to each of the children. And then we can now update the size array by adding up the size of all like the children. For the combination, we're going to like divide again. If you see like the formula over here for the multinomial coefficient, we're going to divide the factorial of the sizes of each of the children, which is what we'll do here. And we'll multiply. The answer is essentially like the product of all these combinations for all the nodes. So that is what is being stored. So we're going to multiply the answer for the subtree of X by like the answer for all of the children's subtrees. And then finally, we'll update it by multiplying by the size of the sum of the sizes of all the subtrees, which will compute like the actual combination. And with that, we can update our answer to include the product of this like multinomial coefficient over all nodes in X's subtree. And then we add our current node X to our size. And then with that, we're done with our first DFS. So now we can go to our second DFS, which is what we'll do like our rerouting. So for this, we'll need to like, again, we'll have the node X and we'll have the node and the parent node. And essentially this will compute what will happen if we transition from the root being the parent node to the root is now node X. So we're going to compute the answer if the root was node X. And to do this, we'll propagate down two values. So this P ans here is essentially like the product of the multinomial coefficients over like all of the nodes in P's subtree. And this is just the size of the P subtree. And here the subtree is defined as if the tree was rooted at node X. And what we'll do is first we'll like essentially we're removing the current multinomial coefficient at X since we'll have to update it. And we'll update it by removing like the current size of the subtree and adding it to include the size of like the new child since P is no longer the parent anymore. It's now the child since X is the root. And then if X is not 0, we can update our answer, right? So the new combination of X is now the total size is now including the subtree of P since P is now a child. And we can use that to update our answer. So answer of X now stores the answer if X was the root. And then now we have to like push this down to all the children. So we'll loop through all the children, which are not like P. And essentially we need to compute the answers of like P ants and P size for the children, right? And we can do this by first, we remove like from the answer all the multinomial coefficients in the subtree of Y. And we'll also remove this from the combination. So we'll essentially like remove that subtree since it's no longer going to be like a subtree of one of our children, right? If we move the root to Y, it'll become the parent. It'll be no longer be the child, which is why we remove it from this combination. And we'll update like the size of the subtree to include all the subtrees except the subtree at Y. And then with this, we're able to like push these values into Y. And by repeating this process, we'll determine the answer for all nodes in the tree. Okay, so now that we have our two DFS functions, we can call them. So the first one to do the initial DP, and the second one to carry out the rerouting process. And then after we've done that, all we need to do is we need to take the average of the answer over all starting nodes. And then since we're counting the number of permutations, we just have to divide by the total number of possibilities to get a probability. And now we can just print out the answer. And so one other thing we shouldn't forget to do is clear our global arrays and variables between test cases. So we can do that. And now let's test our code on the sample test case from USACO. And we can see that it gives us the correct answer. And this solution will get full credit for this problem. And thank you guys for watching. I know this video included a couple of advanced topics like modular inverses and rerouting tree DP. And so I hope you guys learned something new today.